Okay, so I want to sincerely welcome you to yet another training and our network defense series. And we are gradually coming to an end of the training. Like we have said, this week will come to an end. If you have not done your module activities, it is good to try and finish it. Today, we'll be looking at a very interesting topic, but technical. We have some labs that I have sent it to you people. I believe you should be able to do it. I don't know if time permits, we may look at some of them, but it's the topic cryptography. Cryptography, okay? And in this particular topic, we'll be looking at the concept of confidentiality, determining the encryption algorithm used according to requirements, or we're looking at obscuring data, using a technique to obscure data, or we're looking at integrity and authenticity, or we're looking at using hashes, the tools that we are going to be using to hash a file. In fact, that's where the activity is. So if time permits, we'll be able to look at that. Else, I will do that on a separate video so that we don't rush it. So these are some of the things we'll be looking at. Confidentiality. There are two classes of encryption used to provide data confidentiality. We have the asymmetric and the symmetric encryption. Okay? Encryption has two classes, the asymmetric and the symmetric. These two classes differs on how the keys are used. Symmetric encryption algorithm use such as data encryption standard DES or 3DES and advanced encryption standards are based on the premises that what? Each communicating party knows the pre-shared key, which means the sender and the receiver, both of them know the password or the key that is going to be used in the decryption of the data. So that is symmetric. Both parties know the encryption key. Data confidentiality can also be ensured using asymmetric algorithm, including reverse, Shamir, and Adelman, and the public key infrastructure. Okay, so those ones in asymmetric, both the sender and the receiver do not have to use the same key. Okay, do not have to use the same key per se, but in the symmetric, they have to use the same key and they know. So let's look at the two. In the symmetric, it uses the same key to encrypt and decrypt data. But in asymmetric, it uses different keys to encrypt and decrypt data. All right? For symmetric, it uses the key lengths that are short, between 40 bits to 256 bits. So they are short. But for the asymmetric, the key lengths are very long. They use between 512 bits to 4096 bits. Okay? Then for the symmetric, it is faster than the asymmetric in the encryption. Is faster. But for the asymmetric, computationally tasking, therefore slower than the symmetric. So the symmetric is faster, asymmetric is slower. Then symmetric is commonly used for encrypting bulk data, such as in VPN traffic. So bulk data. But the asymmetric is actually used for quick data transactions, such as HTTPS, when you are accessing your bank data and things like that. So that is like the difference between the two. So the symmetric algorithm uses the same pre-shared key to encrypt and decrypt. We said that. So a pre-shared key or a secret key is known by the sender and receiver before any encrypted communication can take place. Symmetric encryption algorithms are commonly used with VPN traffic because they use less CPU resources than the asymmetric algorithm, allowing the encryption and decryption of data to be fast when using VPN. So when using symmetric encryption algorithm, like any other type of encryption, the longer the key, the longer it will take for someone to discover the key. You know, there are devices now that they use in breaking this or doing this decryption. So the key length, it's like permutation. It uses permutation means. So the key length determines how long it's going to take. So when using symmetric algorithms, like any other encryption, the longer the key, the longer it will take for someone to discover the key. All right. So most encryption keys are between 112 and 256. But to ensure that encryption is safe, a minimum length of 128 bits should be used. All right. So that is that one. So for the symmetric, okay. Symmetric encryption algorithms are sometimes classified as either a block cipher or a stream cipher. You know, when you say cipher, means that you are, it's just to encrypt. Decipher means to decrypt. That is just it, right? So block cipher transforms a fixed length block of plain text into a common block of cipher text of 64 or 128 bits. What are we saying? You have a message here in plain text. Cipher means that you encrypt it, you jumble it and encrypt it. All right. So you have this plain text here. It says block cipher encryption is completed in 64-bit block. That is where it turns into this now. So the 64-bit block is talking about using binary. Okay, so that is it. Now, that is the block cipher. But the stream cipher, what happens to it? It says encrypts plain text 1 byte or 1 bit at a time and are typically faster than block ciphers. What does it mean? Here, you see, it takes the whole document and converts it into this using this. But the stream cipher, it picks line by line. It picks byte by byte, and it does the encryption. All right? So that is why it's called stream ciphers. So well-known symmetric encryption algorithms, we have them like the DES, which is Data Encryption Standard. It's a legacy symmetric encryption algorithm. It uses a short key length that makes it insecure for most current users. Okay. Then you have the triple Ds. So we call it DES, the triple DES. All right. It's a replacement of data encryption standard. Okay, but it repeats the DES algorithm process 3 times. That is what it does. Okay, it should be avoided if possible, as it is scheduled to be retired in 2023. But we are in 2024. So if replacement use very short key lifetime, so this is outdated, this is outdated. Then you have the AES, Advanced Encryption Standard. Most of the times we use it in our Wi-Fi. Wireless that. So it's popular recommended encryption algorithm. It offers a combination of 128 to 192 or 256 keys. So most of the times when you are setting up your Wi-Fi password and things like that, that one matters, okay? Matters. Okay. Then you have software optimized encryption. Faster alternative symmetric encryption algorithm to AES. It is a stream cipher that uses 160 bits encryption. All right. And so then last one, the reversed ciphers, RC. Several variations have been developed, but the reverse cipher 4 was the most prevalent in use. All right, so it's also a stream cipher that was used to secure web traffic. So you see in the stream cipher, most of the times is used especially in data in transit. That's where it comes in very handy. So let's look at the asymmetric. For the asymmetric encryption, they are designed so that key used for encryption is different from the key that is used for decryption. So the decryption key cannot in any reasonable amount of time be calculated from the encryption key and vice versa. So what you use, this is the document, and then you carry your encryption and you put it together, then it forms this. And then to decrypt it, you carry a different whatever, and you do with this so that it will transform to this. It's kind of very complex, all right? It's kind of very complex, but it's more secure. Okay, it's heavy to use, but it's more secure. So asymmetric algorithm use public key and private key, and both keys are capable of the encryption process, but the complementary paired keys is required for decryption. So the process is also reversible so that data is encrypted with the public key requires the private key to decrypt. Asymmetric algorithm achieves confidentiality and authenticity by using this particular process. Asymmetric encryption can use key lengths up to this, from 512 to 1496. All right, so remember we said the longer the key length, the more difficult it is to break it. So examples of protocols is the Internet Key Exchange, this SSL, socket layer, or TLS, then the SSH, and then the PGP, pretty good privacy. Okay, these are different protocols and standards that are used in data exchange. All right, so especially for encryption, so it makes it very, very secure. So we have some examples where we have the Diffie-Hellman, very, very popular. It allows two parties to agree on a key that they can use to encrypt the message they want to send together. The security of this algorithm depends on the assumption that it is easy to raise a number to a certain power, but difficult to complete which power it will be used given the number and the outcome, okay? Then you have another one called the Digital Signature Standard, DSS, or the Digital Signature Algorithm, DSC. DSS specifies DSA as the algorithm for digital signatures. DSA is a public key algorithm used on the El-Gamal signature scheme. Signature creation speed is like RSA, but is 10 to 40 times slower for verification. Then you have the reversed Shamir, okay? The RSA or reverse Shamir algorithm is for public key cryptography based on the current difficulty of factoring very large numbers. It is believed to be secure given sufficiently long keys and the use of up-to-date implementations. Okay? Then you have the LGAML. The LGAML used for public key cryptography based on the Diffie-Hellman key agreements. Okay? Now, this is how basically it works. Asymmetric algorithms are used to provide confidentiality without pre-shared key password. The confidentiality objective is initiated when the encryption process is started with a public key. The process can be summarized using this formula. So how does it work? You have your public key, which is the encrypt. You have your private key, which is to decrypt. That gives you confidentiality. So what it means is that when a public key is used to encrypt data, the private key must be used to decrypt it. Only one host has the private key. Therefore, confidentiality is achieved. Now, when we say private key is not something that is routable over the internet. The public key is what is routable, is what you can see, what is globally seen. So even if you get that one, you don't have the one for the local machine, the private key. Okay, you don't have that one. So you need the combination of the two to be able to decrypt. Okay, so we have an example, Bob and Alice data exchange. This is Alice. She's saying, can I get your public key, please? And then Bob sends his public key. So Alice will now use her own private key plus Bob's public key and then encrypt it and then send it. And then Bob, to decrypt it, he will use the public key and the other private key. All right, this is how it works. So Alice uses Bob's public key to encrypt a message using an agreed algorithm. So this is the algorithm here. This is Bob's public key. This is the message. And then once it's encrypted, it gives you this. Bob then uses his own private key to decrypt the message. His own private key to decrypt the message. All right. So that is how it is done. So the authentication objective of asymmetric algorithm is initiated when the encryption process is started with the private key. So the process can be summarized using this formula. Private key plus public key will give you the authentication. So one is used to encrypt, the other is used for the decryption. So when the private key is used to encrypt data, the corresponding public key must be used to do the decryption. So only one host has the private key. So only the host could have encrypted the message, providing authentication of the sender. So when the host successfully decrypts the message using a public key, it is trusted that the private key encrypted the message, which verifies who is the sender. So that is how it particularly works, right? So Alice encrypts message using her private key. This is Alice. And then Alice sends the message to Bob. All right? Alice sends to Bob. But before she sends to Bob, says, can I get your public key, please? This is Bob now asking. And then, okay, let's start from here. Let's start from here. What did it say here? You see, Alice, this is Alice's private key. And then with Bob's public key here. And then the message is encrypted. And then it gives here. For it to decrypt, Bob, can I get your public key, please? And then you have Alice, public key here. And then she sends her public key to Bob. Bob requests Alice's public key to authenticate the message. And once it does that, that is where the authentication happens. Okay? So, this is just, okay. Now, let's continue. Combining the two asymmetric encryption process provide message confidentiality, authentication, and integrity. The following examples, a message will be ciphered using Bob's public key, and a ciphered hash will be encrypted using Alice's private key to provide confidentiality. Okay, this is the message. This is Bob's public key plus Alice's private key. And then the message then is encrypted. But if it comes the other way, Bob and Alice will have to do the integrity exchange. Alice also wants to ensure message authentication and integrity. So authentication ensures Bob that the document assures Bob that the document was sent by Alice. And integrity ensures that it was not modified. So Alice uses her own private key to cipher a hash of the message. So Alice sends the encrypted message with the encrypted hash to Bob. And that is what happens here. You have Alice's private key plus the hash, encryption algorithm, and then you get this. Okay? So I want to believe we now get the concept of it. You definitely need the public key and the private key. All right? For both encryption and decryption. Diffie-Hellman, an asymmetric mathematical algorithm that allows two computers to generate an identical shared secret without having communicated before. That makes sense. They have not talked before, but they will create and generate an identical shared secret. That must be really, really serious. So the new shared key is never actually exchanged between the sender and the receiver. However, because both parties know it, they can be used by an encryption algorithm to encrypt that traffic between the two systems. Here are two examples of the Diffie-Hellman that is commonly used. Data exchange using an IPsec VPN or SSH data exchange between sender and receiver. So this is how the Diffie-Hellman works. It's like the colors in the figure will be used instead of the complex long numbers to simplify the Diffie-Hellman key agreement. So this is, for instance, Alice. This is Bob. Now look at what is done here. Our target is for us to understand how the exchange does. You see, the agreed color is this yellow. So both the sender and the receiver know the agreed color. Then each one of them is mandated to have their own secret password. So Alice have her secret password, Bob has his secret password. So you see, they all agreed on the color. Everybody has a secret password. Then you mix it. If you mix these two, the color and the secret password, it gives you maybe orange color. This is now going to be the public key for Alice. This one is going to give you green. It's going to be the public key for Bob. Now, that is what they are going to use for exchange when it goes to decryption. They want to go and decrypt it. What is being exchanged is this mixture, the mixture of this guy and this guy. That is what they exchange. But remember, this mixture is a combination of two things here. It's a combination of two things. So if you do the mixture, at the end of the day, you will get the same result. Because all you just need to do is just go and you know the agreed color. Go and take out the agreed color and you'll know what is left there. Okay? So the security of Diffie-Hellman uses very high large numbers in its calculations. The higher group numbers are more secure, but require additional time to compute the key. So the following identifies the Diffie-Hellman group supported by Cisco iOS software and their associated prime number values. Okay? Obscuring our data. Data masking techniques. Data masking technologies secure data by replacing sensitive information with non-sensitive version of it. The non-sensitive version looks and acts like the original so that an organizational process can use non-sensitive. So sorry. The network fluctuated a little, but I think we are back now. So okay, so sorry about that. So let's continue. So still talking about integrity and authenticity, okay? Securing communication. Organizations must provide support to secure internal and external traffic. The 4 elements of secure communications are data integrity, or origin authentication, data confidentiality, and then data non-repudiation. Now let's look at them. When you say data integrity, what are we talking about? That just guarantees that the message was not altered, and any changes in the data transit will be detected. Integrity is ensured by implementing either the SHH2 or SHH3, which is the message digest algorithm. All right. So it's like I send you 5,000 naira, and you need to confirm you received 5,000 naira. If I send 5,000 and you receive 4,005, then you know that there is a problem. There's no integrity in the message. 2, origin authentication guarantees that the message is not a forgery and actually comes from whom it states. Many modern networks ensure authentication with algorithms such as hash-based message authentication codes. So these days, this issue of phishing as a problem. People get emails from banks, but fake banks, not genuine and things like that. They're just phishing. So you need to authenticate it. Data confidentiality guarantees that only authorized users can read the message. If the message is intercepted, it cannot be deciphered within the reasonable amount of time. So data confidentiality is implemented using symmetric and asymmetric encryption algorithm. Okay, now data non-repudiation guarantees that the sender cannot repudiate or refute the validity of the message sent. So non-repudiation relies on the fact that only the sender has the unique characteristics or the signature for how the message is treated. Hashes are used to verify and ensure data integrity and is based on one-way mathematical function relatively to compute, but significantly harder to reverse. Okay. The cryptographic hash functions can also be used to verify authentication. A hash function takes a variable block of binary data, which is message, and produces a fixed length, which is condensed representation. With hash functions, it is computationally infeasible for two different sets of data to produce the same hash output. So every time the data is changed or altered, the hash value also changes. So the cryptographic hash function is applied in many different situations for entity authentication, data integrity, and data authenticity purpose. Cryptographic hash operation. Mathematically, the equation that you see here, H is equal to Hx, is used to explain how the algorithm works. When we say H equals to Hx, the small h is just the hash value. Yeah? Because that is supposed to be the output. That's the hash value. So this hash value is just a combination of this hash function and the arbitrary length. So that's basically what it is. Okay. Then the MD5 or the SHA hash functions are used to ensure message integrity that has not changed accidentally or intentionally. Deliberate changes that are made by the threat actor are still possible. Okay. So hashing can be used to detect accidental changes, but cannot be used to guard against deliberate changes that are made by the threat actor. Therefore, hashing is vulnerable to man-in-the-middle. This is man-in-the-middle attack. Okay? And does not provide security for transmitted data. So we have the SHA-1, 2, and 3. What is the difference between all of them? Is the size. You see this one creates a 160-bit hash value. Okay, and then HS2 creates up to 224 bits. Between 224 to 512 bits. But SHS3 is the newest hashing algorithm and an alternative and eventual replacement for the SH2 family. Okay, so what it does, it uses, it includes from 224 bits, 256, and 384. So what do you observe? That the size of the bits is increasing. But if you look at the MD5, basically it's just 128. So there are instances you use the higher values of encryption, but know that once you are using that, it will weigh down your system a little bit, but you get more secure. Okay. Origin authentication uses a key hashed message authentication code to add origin authenticity and integrity assurance. The HMAC uses an additional secret key as input to the hash function. Okay, so all this is just to explain to you how the encryption takes place, how the hashing algorithm takes place, how it works, and how it combines certain elements or key values together to give you what you need. So an HMSC is calculated using any cryptographic algorithm that combines a cryptographic hash function with a secret. So you need a secret key, and then you add the hash function before you get your hash value. Okay, so these are just examples on how it works. So let's see using hashes. Now we will try and see if we can do an activity. I think this is the last one. If we're able to do it, then we do this activity. Integrity ensures that data and information is complete and altered at its acquisition, which means from the time you are sending to the time you are receiving, nothing alters. So to verify the integrity of all iOS images, Cisco provides MD5 and SH checksums, and it's downloaded at the portal. All right, so user can make a comparison of this MD5 digest against the MD5 digest of a Cisco iOS image installed on a device and can feel confident that no one has tampered with it. Okay, so we're going to see how it works. So the field of digital forensics uses hashing to verify all digital media that contains files. For example, the examiner creates a hash and a bit-for-bit copy of the media containing the files to produce a digital clone. The examiner compares the hash of the original media with the copy, and if the two values match, the copies are identical. The fact that one set of its bits is identical to the original set of the bit establishes fixity. Fixity helps to answer several questions. Does the examiner have the files they expect? Is the data corrupted or changed? Can the examiner prove that the files are not corrupt? Now, the forensic expert can examine the copy for any digital evidence while leaving the original intact and untouched. Hashing passwords. Hashing algorithm can turn any amount of data into fixed length, fingerprints, or digital hash. Nobody can reverse a digital hash to discover the original input. If the input changes at all, it results in different hash. This works to protect passwords. A system needs to store password in the form that protects it and keeps it away from prying eyes, while also being able to still verify that the user password is correct. Okay, so the diagram shows the workflow for user account registration and authentication using hash-based system. So you have a user that is creating the account. The system hashes the passwords and stores the hash in the database. So that means even if you have access to the database, you're not going to see the password in plain text. It's going to be hash. All right. So that is it. So when the user logs in with the same name and password, the system compares the hash value of the password entered by when it's stored. That is the point. So how do you crack it? To crack a hash, an attacker must guess the password. So the top two attacks used to guess passwords are dictionary and brute force attack. Dictionary means that it uses a file containing common words or phrases and passwords. The file has the hash of 3 common passwords calculated. It compares the hashes in the file with the password hashes. And if the hash matches, the attacker will know the group of potentially good passwords used in the system. So that is one way. The other way is the dictionary. The other way is the dictionary, the brute force attack. You know, when you keep trying multiple passwords over and over and over and over. So it attempts every possible combination of characters up to a given length. It takes a lot of processing power at a particular time. But in theory, it's just a matter of time before the method is actually being discovered. Salting. Salting makes password hashing more secure. If 2 users have the same password, they will also have the same password hash. A salt, which is a random string of characters, is an additional input added to the password before hashing. This creates a different hash result even when the 2 passwords are identical. So when database stores both the hash and the salt, the same password generates a different hash for different users because the salt in each instance is different. Meanwhile, the salt does not have to be secret since it's just random. Okay? How do you prevent attacks? Salting prevents an attacker from using a dictionary attack to try to guess the password and make it impossible to use a lookup table and rainbow tables to crack the hash. What is this lookup tables? All right, it stores a pre-computed hash passwords in a password dictionary along the corresponding passwords. Okay, the reverse lookup table is an attack that allows cyber criminals to launch a dictionary brute force attack on many hash without the pre-computed lookup table. How about the rainbow tables? They sacrifice hash cracking speeds to make the lookup table smaller. So the smaller table means that the table can store the solutions to more hashing. So basically, you have ways to prevent and you have ways that they can use to break it in. Okay. So this is where we will end our lecture for today. Let me load up the lab activity. Just a minute. Just a minute. Where's the lab? Okay. Okay. All right, so I've loaded it. Let me share it with you so that you'll see what we're doing. All right, so this is the lab activity. This is the lab activity for hashing things out. And the objectives of this activity is hashing a text file with OpenSSL and then verifying the hashes. What is the scenario? It says, let me zoom it this way. It says Hash functions are mathematical algorithms designed to take data as input and generate a fixed size unique string characters known as the hash. Okay, designed to be fast, hash algorithms are very hard to reverse. It is very hard to recover, and the data that created by a given hash. So based on the hash alone. Another important property of hash function is that even the smallest change done on the input yields a completely different hash. So while OpenSSL can be used to generate and compare hashes, other tools are also available. Some of these tools are also included in this lab. So what we need is a security workstation or a virtual machine. Okay, you have a virtual machine, a computer. So hashing a text with an OpenSSL. So OpenSSL can be used as a standalone for hashing. So to create the hash file, follow the steps below. In the security workstation virtual machine, open the terminal window. So we need to download the virtual machine. Okay, so let me get that one for us, and then we will open it so that you see what I mean. Right, right. Trying to, where is it? Sorry, it's a little bit slow. You should be able to have it on your portal. I wanted to just download and use, but I prefer we do it together so that you will learn and understand. So just a minute, please. Join you guys. Network defense. There you go. Okay, it's still downloading, but it's kind of very, very slow. How do I hasten this? I'll delete the one I've done, and then we do it afresh. So this is just the lab activity. And in the lab activity, we're supposed to have this virtual machine, and it has the operating system. It has all that we need to do the lab activity. So you would have logged in, and all we'll just need to do is be running this command. You run this command, and then you run this command, and then I will be explaining to you. If you run this command, in Linux, once you see CD, is like change directory. So what this is saying, it says, first of all, in security workstation virtual machine, open the terminal window. It's going to open for you a particular window. It says, because the text file to hash is in this directory. This directory means the location where it is stored. All right, the location where it is stored. So we are supposed to now locate it. So we now change the directory. Look at it here. Home analyst, and then this is the file. This is the file. Then for us to now open the content of the file, we use this command cat for us to read the content of the file. Okay, and then once you read it, it's going to come out in this particular way. Now, our activity is this particular message like this. We are going to encrypt it. And once we encrypt it, it's going to create a hash value. Look at the hash value. It's going to create a hash value. And once it creates that hash value, then we're going to now tamper with it. And then we will now see whether the hash value will be the same. This is the new hash value. You will see it. All right. So you will see the question that is going to ask you. It says, is the new hash different from the hash calculated above? And the answer will be yes, because if you see this value that is created, it's going to be different from this value that was created. Why? Because there was a little change in the document. So if the document is altered, it's going to show. So that is what this activity is just all about. It's just to tell us that you can have a hash value created. And once you have your hash value created, if it is altered, it can be known. So for the purpose of tomorrow's class, I will take my time to download it again. And then, but I will not configure it this time around. I'll wait when we come on class, then we will do the activity together and you will see what I mean. So this is where we're going to draw the curtain for today's class, unless maybe there's anyone who has any question that we need to look at. Okay, if you have a question, then you let us